Aloha class. What I'm doing here is I'm going to go through these solutions, and it's going to be fairly quickly, okay? But in case there's any errors or things that I want you to focus on, I thought it could be helpful, okay? So we're going to start here, okay? First page. What is the definition of continuity at this point? Okay, remember that f of x is going to be continuous at x equals c if this is true or this. Now, please remember that this means the same thing as this piece here. Okay, and remember, in essence, what it's talking about is you have a limit that goes to the same height from the left and to the right, and then the f of c part means at c we're coloring in that. Okay, they ask us in part 2 to draw examples of where f of 5 exists and the limit does not. Okay, that would be one where you have a jump discontinuity, okay? B, and I'm not going to take too long with all these. I think I'll focus on the ones where I think would cause you guys the most trouble, okay? If you look at part 2B, there would be an example of where a limit does exist, but the value does not, okay? That'd be, remember, a removable discontinuity, okay? All right, here we go. Example 3, and I can't get it all in here. But what example 3 really talks about, okay, is that at this value at x equals 1, there's something going on there. The limit does exist, right? The limit actually equals 0 from the left and right, but the function value is down here. That is an example of where this particular function, g of x, does not exist or is not continuous. Okay, I should say it does exist there, but it's not continuous, okay? Even though the limit works out, the function value does not. So that's where that falters, okay? And then we have this piece over here. Let's examine that. That'd be at x equals -1. At x equals -1, from the left, my answer is 1. From the right, my answer is 1. But there's no value there. There's actually no value anywhere. So even though the limit exists, since you don't have a function value, we say it's not continuous there either. All right, where else is it maybe not continuous for g of x? Booyah, something happens there. And believe it or not, this one fails immediately. The limit from the left, as we approach 0, is -1. The limit from the right equals 1. So this is -1, that's 1. That's called a jump, right? There's no way that works out. So this guy's not continuous either. And I could put a function value here. I could put a function value here. The jump still makes it where it does not work out, okay? So those are all cases of where a limit does not exist, is not continuous, okay? So you might be asking yourself, where is it continuous? Well, it's continuous from -2 to -1. It's continuous, not there and not there though, right? It's continuous from -1 to 0. It's continuous from 0 to 1. It's continuous from 1 to 2. And we would include 2 because it's colored in there, okay? Now, it's very important, remember, to what this looks like pictorially, okay? Pictorially a word? It is now. All right, here we go. Number 4. Okay, I'm just going to see how the work is presented here. We want to know if this is continuous at 3. At 3, we were dealing with a parabola, and we're dealing with a line. Those guys are continuous everywhere, so it just might jump there. So we use the definition of continuity. Nicely done. The parentheses around these guys, right? Beautifully done. So when a is equal to 4/3, good job, good job. Right, guys, I'm just checking the work here. Unless there's a little mistake mathematically, it looks like these solutions are good to go. Number 5, hopefully you're working on these at home. Let's see. Ooh, this is a line in a line, right? That's what we're dealing with here. Ooh, sorry, I need to know where my pen was. That's a line in a line. So the question is, do they connect at 2? So once again, definition of continuity. These guys should be in parentheses, right? Because you're taking the limit of the quantity. K is equal to 3. If K is equal to 3, you have a line that, and that would be colored in, that matches up with a line. Okay, it'd be some type of scenario like that. That work is beautifully done, you guys. All right, let's keep rolling. All right, let's see. Here's number 6. Ooh, number 6, we're dealing with a parabola. Ooh, no, right? We're dealing with that. That's a parabola and a parabola. It looks like one of those parabolas would be going up. Another one of those parabolas would be going down. But guess what? We do the same thing. Definition of continuity. Ooh, plus or minus 2. So here you get two instances of what A could be where these graphs match up. Okay, make sure, right? Come in early for help, come in for Google Meets early, and I will come and help you out. I don't want to make these solution checks the longest thing ever, all right? So I'm not going to do all the problems by yourself. You have the work right here. Okay, it says do something else, see attached. Oh, yeah, because when you do the limit here, oh, no, she doesn't have it written. So I'm guessing it's on our attached. All right, let's go to the attached. Ooh, booyah, here we go, sweet. So there it is. So you're going to do the limit from the left and right. But if you notice for this problem, and I'll go up there a little bit, but there was no left and right, right? There was just that we're going to use this piece here when x is not 2. All right, so if we need to know where it goes. And to find out where it goes, we're going to do our little conjugate work, and we get 1/6. So this is a removable discontinuity. So if I come back up here to number 7, there is going to be a removable discontinuity at 7. Once again, we did not have to do it from the left into the right because the left and the right are the same thing, right? We're going to use the same piece. So if you were wondering what the issue was there, that is what it is. But we need the 1/6 equal k plus 3. So this is where this work comes in. And if k is negative 17/6, we color in that removable discontinuity, thus making it now continuous. So we are good to go. Remember, she doesn't really write statements here. I gave you a statement to write down in class. Continue to justify your response by making statements, and in these instances, using the definition of continuity. Okay, here we go. Number 8. Here, what are we trying to do? Oh, definition of continuity again. Okay, and this is the one where we are going to create, okay, kind of like a new function. But in this case here, same situation. It says we're just going to use the main piece when x is not negative 2. So we don't have to do a left and a right. We just have to do that the limit is equal to the function value. Right? If we do this work, parentheses should be there, we get negative 4. So guess what? We need the function value to equal negative 4 and able to fill in that hole. By the way, BT dub, right? This is how I could create a brand new piecewise function where it would be continuous everywhere, right? And you know what? The fancy way of writing x minus 4, you could have looked really cool and just put x minus 2 there. Some students like to be cool, all right? And then you plug in that and you still get a negative 4, which is the same thing, but it's a fancier way to represent a piecewise function in this regard. All right, I think we're going to have a couple practice problems. Ooh, number 9. Number 9's a piece of work, right? If you look at number 9, you have all of these pieces, and those are continuous everywhere, everywhere. Sine's continuous, parabola is continuous, line is continuous, a line is continuous. So the only thing that could mess it up are where we could maybe jump. Okay, you could jump at 0, right? Because from the left you use this, from the right you use this. So that's this work right here. And everything equals 0. So they're connected. Sweet. All right, next one. At 1 you could jump because from left you're using that, from the right you're using that. That's this piece right here. Oh, sweet. Everything equals 1. That means it's continuous at 1. We don't jump. And the last one, you could also jump at 2 because you go left is this, right is this. Oh, snap. My face is in the way. But if I move up a little bit, I notice that I actually jump in this situation. How do I know I jump in this situation? The values aren't the same, so that means it would not be continuous there. And that's what that question was asking. Okay, piecewise function, the functions are all continuous, but maybe at those values it could jump a little bit, right, class? All right, let's keep going here. We're doing great. Oh, so we have a couple here, 10A, 10B. It says see attached work. These are examples of removable discontinuities because if you notice, if I plug in this point into there, I get 0/0. That means a removable discontinuity. If you plug a 4 in there, I get 0/0. That means a removable discontinuity. Both of these scenarios would look like that. And then what we are doing is we are going to create brand new piecewise functions here that tell us to use our cool function when it's not 0 or not 4. Why? Because those gave me 0 over zeros. But use this special thing to color it in, right? And now it's continuous. To color it in, and now it's continuous, all right? I'm going to look at her work just to make sure you wouldn't lose any points on a quiz or test in my class, all right? So let's go ahead and zoom down here to the end to number 10. Oh, here's 10A. Let's check it out. Yep, you guys should hopefully know this already. I'm allowing you to use a cheat. You've got to bring that out until that last step. Okay, you have to. Okay, if you don't do it, you'll be mad at me. So I hope you guys watch this video. All right, let's check the other one. Let's see your work. Monies, I would just say put parentheses around that. Okay, there should be parentheses there. All right, class, let's go ahead and get this done. I don't want these solution videos to run too long. Okay, good. Question 11, look at it. I'm not going to talk about it too much. It's just kind of cool how it works out. I see a lot of students generally get those problems wrong. All right, 12 is a good one. It kind of brings the whole chapter so far together. All right, we got a domain. Please remember that these guys should not have a tail on it, okay? But it's going to be good everywhere to go except -5 and -2 because those values are not in the domain. They will actually give me a DNE, okay? And it's important to understand what is the result of each of them. If you look at -5 as a limit, you get that, which means it's DNEY because there would be a VA, a vertical asymptote, okay? But if you look at -2, okay, if you look at -2, you get 0 over 0. That means there is a removable discontinuity at -2. And where does this go? Where does it go? Right? Where does that go right there? I can't see it, but I think it says, what would that be? It'd be 1 over 3. I think it says at 1/3. So it goes to a height of 1/3. So that's going to be important because this question is going to ask me to extend this problem a little bit more. So let's see what the next question says. Are there any horizontal asymptotes? Remember, class, that's M behavior. So that would be x squared over x squared, which is 1. So there's a horizontal asymptote at 1, which means the limits as we go to infinity or -infinity will go to the horizontal asymptote. I love this question. Brings up almost everything we've learned so far. Are there any vertical asymptotes? Remember, that means a vertical asymptote. I kind of said it earlier. So at x equals -4, there's a vertical asymptote, which means we could inspect it from the right. We could inspect it from the left. Does it even, ooh, there's a right one, but I don't think they have it. So remember though, you should inspect it from the left and right, but only if they ask you to do so. In this problem, they actually don't. So she just probably put that there for a, did you remember? Okay, and then the last one, they want to ask us to write an extension. Remember, you cannot fix a jump discontinuity. You cannot fix a infinite discontinuity or a vertical asymptote. So the only thing that I am able to fix is this guy, right? How do I fix that guy? Well, we did it earlier, remember? We did the limit, and the limit equaled 1/3, so we fixed that. So -5 we can't fix, right? It's a vertical asymptote. So we're going to tell this function, this computer, to use the top piece everywhere except these two pieces, because it will give me a DNE. But guess what? This cool little computer right here, it will get fixed because it's going to put in a 1/3 for it. The -5, we're out of luck, right? We're just out of luck, okay? Now the last two pieces have to deal with the ridiculously important IVT, the intermediate value theorem, okay? And 13 here, let's see. Intermediate, it says, without using a picture, tell me why this dude right here has a 0. Has a 0. It's a parabola. Parabola is continuous everywhere, right? We know that. We can actually assume that, okay? But does it have a 0, okay? In between 2 and 4. How do I figure that out? Well, let's find out what f of 2 is. Let's find out what f of 4 is. Oh, snap. If f of 2, if I just look graphically, right, and this is why they say without using a picture, 2 comma -1, 4 comma 3. How does it get from there to there? The question is, how does it get from here to here if it's continuous? And parabolas are continuous, so the only way it can get there is spling. Whoa, spling. It's got to cross the x-axis, therefore it has to have a 0. So we write a fancy statement. Since f of x is continuous, and it's got to be continuous, that's the hypothesis of the IVT, and that's less than 0 and that's greater than 0, then it's got to cross 0. The IVT proves it. Okay? IVT, very important, intermediate. It really means if you are dealing with a continuous function, intermediate, in between the two endpoints, everything's got to get hit. And in between -1 and 3 is 0, so that gets hit. 2 gets hit. 1.5 gets hit, right? Everything in between will get hit. The IVTs proved it, right? All right, here we go. Let's do this guy. Same thing, IVT question, but this one says here, does it have to equal 3 at least once? Well, booyah, booyah. Well, it's continuous, right? Booyah, booyah, -3 to 5. If it goes from -3 to 5 and it's continuous, does it have to hit 3 for sure? So then just make sure you write a statement. Okay, let's get this video here done. Remember, these videos you can fast forward. They are not on Edpuzzle. All right, h of x. h of 0 means I use the top piece, right? H of 0 means I use the top piece and I get -4. Okay, h of 4 means I use the bottom piece. I get 21. Okay, it says from 0 to 4. There is no such value of x that h of x equals 10, even though, what? Explain why this result does not contradict the IVT. Well, the only way that this situation could happen is if it's not continuous. So what should we do? We should check. This is continuous everywhere. This is continuous everywhere, but maybe not at 2. So what do we do? Boom! And guess what that means? It jumps. It jumps. Okay? So even though you could have got tricked right there, right? You get a -4 for one endpoint, you get 21, everything gets hit between, right? No. Not if it's not continuous. And this is a piecewise function, which should throw up a red flag. And guess what? It's not continuous everywhere. All right? And that's exactly why it doesn't work out for that one. All right? Let's keep rolling. And that is it. Aloha. Let me know. Give me some feedback. Do you guys like me going over the with the solutions with you? Let me know. And if you do, I will try my hardest to make that happen for you guys. Aloha.